Hey there and welcome. Have you ever just stopped for a second and thought about what's actually going on inside your phone or your computer? It's all this incredible magic built on a language that only has two letters, a 0 and a 1. So in this explainer, we're going to pull back the curtain and figure out why this ridiculously simple system is the secret sauce behind all of our amazing, complex technology.
I mean, it doesn't really make sense at first glance, does it? We've got these machines that can create entire virtual worlds and talk to anyone on the planet in an instant. But at their core, they're speaking the simplest language you could possibly imagine. So how is that even possible? And, why do it that way? That's the big mystery we're cracking open today.
All right, so to really get our heads around this, we actually need to take a step back and look at something we all use every single day without even thinking about it: our own numbers. Turns out, the way we count is just one way of doing things. That's right, the whole system we use, with 10 different digits, 0 through 9, it's not some universal law of math. It's a human thing. And the most popular theory is that it all started because we had these handy, built-in calculators at the ends of our arms, our 10 fingers. It just made sense. So let's quickly break this down with a number like 263. See, it's not just a 2, a 6, and a 3 sitting next to each other. As you can see in the table, it's really 2 hundreds, 6 tens, and 3 ones. Every column you move to the left is worth 10 times more than the column to its right. Now, this idea of place value is the absolute key here. Remember that.
And here's the thing, this works with any base. The ancient Babylonians, for example, they used a base 60 system. That's actually why we still have 60 seconds in a minute. The math works perfectly. So if our base 10 is really just a human habit, what are computers using?
Well, let's use that exact same logic for the language computers speak, binary, or base 2. Instead of powers of 10, everything is based on powers of 2. So the places become the 1s, the 2s, the 4s, the 8s, and so on, doubling each time. So if we look at the binary number 1101, it's 18 plus 14 plus, 0 2s plus 1 1, which adds up to the number 13 in our system. Simple as that.
Okay, so we've established that the math totally works. It's a legit way to count. But that brings us right back to our big question. Out of all the possible options, why on earth did the pioneers of computing pick the absolute simplest one? Well, the answer has nothing to do with pure math and everything to do with the real world.
We could have tried to build a computer that thinks in base 10. In fact, people did try. Some of the very first inventors attempted it, but they ran headfirst into a massive fundamental problem that made those early designs super unreliable.
You see, computers run on electricity, and trying to get a wire to reliably hold 10 different distinct levels of voltage for the digits 0 through 9, well, it's a total nightmare. Electrical signals get weak, they pick up noise, they're affected by heat. A signal that's supposed to be a 9 could easily droop a little and be misread as an 8. And in computing, that's not a small mistake, that's a catastrophe. The solution they came up with is just brilliant. Think about the difference between a light dimmer and a regular light switch. The dimmer is analog. It has a whole range of maybes in between. But the light switch, it's digital. It's either on or it's off. There's no kinda on. It's a clear, simple, unmistakable signal. And this quote just nails it. With a two-state system, it doesn't have to be perfect. As long as the voltage is high enough, we call it on. If it's low enough, we call it off. All that messy, noisy space in the middle, we just ignore it. This simple, clear distinction is what makes all of modern computing possible. And this is where it all clicks. This is the bridge. That physical state of a switch being on, or a high voltage, becomes the abstract idea of a 1. The physical state of a switch being off, or a low voltage, becomes the idea of a 0. That's it. That's the fundamental link between the physical machine and the software it runs. So we have our super simple, super reliable on-off switch. But how do you get from that to streaming movies, playing games, and everything else we do? Well, you do it by combining millions and billions of them. Each one of those little on-off switches, each individual 1 or 0, is called a bit. Think of it like the atom of the digital world. It's the smallest possible piece of information you can have. Now, one bit by itself can't represent a whole lot. So what do? We string them together. And the most common way to do that is to group them into a team of 8 bits. And we call that a byte. And this is where the magic really starts to build.
With just those 8 little on or off switches, you can suddenly create 256 unique different patterns. That's enough to represent any number from 0 all the way up to 255.
So here's where it all comes together. We can just create a code book. Using a standard called ASCII, we all agreed that the number 65 would represent a capital A. So whenever the computer sees the byte pattern 0100001, it knows, that's a capital A. The number 97, that's a lowercase a. And you just do that for every letter, number, and symbol you can think of.
And from there, it just scales up and up and up. You group bytes together to represent the color of a single pixel in a photo. Millions of bytes store the photo itself. Billions of bytes can store a whole song or a movie. Every single piece of digital stuff you've ever touched, including this very explainer, is, when you get right down to it, just an incredibly long list of ones and zeros.
So let's bring it all home. The reason computers use binary isn't because the early engineers were trying to be difficult. It's the exact opposite. They found the absolute simplest, most elegant solution to a really complex, messy physical problem.
And this quote from the mathematician Stan Gooder just says it all. The real world is messy. Electricity is messy. By choosing a system with absolute clarity, on or off, high or low, 1 or 0, engineers created this rock-solid foundation that our entire digital world could be built on top of. It really is a triumph of simplicity.
And that kind of leaves you with a really cool thought, doesn't it? The whole story of binary shows that sometimes the most powerful solutions aren't the most complicated ones. They're the simplest and most robust. It really makes you wonder, what other huge, messy challenges out there are just waiting for us to find their fundamental on or off switch? Thanks for watching.